Hi, my name is Manish Gupta, and in this video, I'm going to talk about these Google models, UL2 and Flan UL2, which are about unifying language learning paradigms. So let's get started. In fact, let's start with this notion of mixture of denoisers, right? And even before that, let's talk about three popular denoising strategies which have been used in several pre-trained language models, right? So these are these three objective functions: causal language modeling, prefix language modeling, and span corruption. So span corruption is the most common one, right? BERT uses it, T5 uses it. So the idea is that you have some sentences or input text and you basically mask out approximately 15% of those things. And the target is essentially, of course, those mask tokens. So you want to predict for those mask tokens, predict the right token for those masked placeholders. Right? Typically the sample efficiency is very poor, which basically means that you try to compute loss only for those positions which are masked. On the other hand, you have causal language models, which are what are used in GPT. So here there is no input as such, but then the target is text. So you want to do next word prediction kind of stuff. And then the sample efficiency is great because you are trying to predict every token in the entire sequence. Right? Then there are prefix LMs, where the input is text up to position K, and then you want to predict text after position K. For example, UniLM, right? So here the idea is that you want to sort of predict text after position K, and therefore sample efficiency is in between. So sequence length minus K. Okay. So these are three different kinds of popular pre-training strategies. Now, which one is better, right? So in the sense, and can we combine these is the question. Okay. To be able to do that, UL2 model actually uses something called as this mixture of denoisers strategy. So let's understand what are the three denoisers that this UL2 model includes or has, right, as part of its pre-training strategy. So there are three different denoisers: R denoiser, S denoiser, and X denoiser, which is also what is shown in the animation that you see here. Right. So the R denoiser essentially follows the standard span corruption. So this span corruption is the same as R denoiser in that sense. Uh, Basically you mask out 2 to 5 tokens, 15% of the input tokens are actually masked out. Right? Now it is S denoiser. So S denoiser is very much like prefix language modeling. So the idea is that it's a sequential span. So unlike in R denoising, where you can actually have non-contiguous spans and then you can mask them and then you try to predict them as part of target, right? In S denoising, it's sequential denoising, where the idea is that it uses prefix LM, which basically means that you take the input, you partition it into two subsequences, and then you use the first one as context and then the second one as the target. Okay. So the target tokens cannot rely on future info. They can be conditioned only on the past info. So therefore, it is more like prefix language modeling. The third one is extreme denoising or X denoising. So here the model must recover a large part of the input given a small to moderate part of it. So as you notice in R denoising, the spans that are masked are very small, but in R denoising, the spans are very large in general, right? So now, in fact, this can be done in two ways. Either the spans are very large or there are too many such spans which are masked out, which basically means that about 50% of the input is masked, not 50%, right? So long spans or large corruption rate is what is common in X denoising or extreme denoising. So extreme denoising can be considered as something in between span corruption and causal language modeling, because causal language modeling is like the full sequence length that has to be generated. But in span corruption, well, 15% of the tokens are masked. Right? So X denoising is something in between. These three denoisers are also shown in the animation here, as you can see. So this is S denoising being done. So you mask out the second part and then you try to break the output. X denoising, some parts, large parts are masked out, right? Or large number of tokens are masked out, as you see, right? Or here is our typical R denoising, which is the span corruption, right? So basically those choices are actually shown in the animation as well. Okay, so how is this Google's UL2 model trained? So UL2 stands for Unifying Language Learning. The idea is that there are these three things that we talked about: language modeling, span corruption, and prefix LMs. UL2 tries to unify all of these three different paradigms of pre-training, right? So we've already talked about these three on the previous slide. Language models is causal language models, span corruption is the same span corruption guy that we talked about. And then prefix lm is prefix lm, right? Where basically you have the prefixes and as input, and then you want to generate the output, generate the sequence after that, following the prefix. Okay. So the way they unify these three different paradigms is to actually express these three paradigms in a single span corruption function of some sort, which takes three parameters, mu, r, and n. Mu here stands for the mean span length, r is the corruption rate, and n is the number of corrupted spans. The idea is that the lengths of the spans are actually sampled from a normal or uniform distribution based on mu. So with the mean as mu. Right. Now, given this definition of span corruption, you can actually express your causal language model using mu equal to L, where L is the overall length of the sequence, R equal to 1 because you are corrupting everything, right? Causal, right? So essentially you're trying to predict everything in that sense. N equal to 1. So number of corrupted spans. So well, there is only one span. That's the whole sequence that is sort of corrupted, and you have to predict the entire thing, right? On the other hand, you can actually also express prefix lm as follows. So mu equal to L minus P, where P is the prefix length. So prefix you don't mask, right? So therefore, except for the prefix, everything else you mask. So therefore, that's the mu, right? And R is so corruption rate is 1 minus P by L, right? Because you've sort of not masked P. So and the total length is L. So therefore, your corruption rate is 1 minus P by L, and N equal to 1 because there is only one, one span that you're masking out. So the final objective in UL2 essentially makes use of this function, span corruption function, and the final objective is a mixture of 7 different denoisers, okay, where which have been obtained from these three different types, RS and X, right, with the different settings for mu, R, and N. Okay, so it is as simple as that. Now, besides this pre-training strategy, which basically involves these 7 different denoisers, so to say, belong to three different types, UL2 also includes a special token for mode switching. So as you noticed in this demo as well, in this animation as well, there was a special token which is also passed as part of the input, so as to tell whether X denoising is being done, R denoising, or S denoising is being done. So it also turns out that depending on the downstream task, one of the denoisers may be more meaningful at fine-tune time. Okay, and therefore this is what is called as mode switching. So which denoiser to use at fine-tune time depends, or rather can be explicitly told to the model by providing this extra token. And therefore, this extra token is provided not just during pre-training, but also during fine-tuning and downstream few-shot learning as well. Right? So basically, by giving that extra token in the beginning, whether it is R, S, or X, you can actually control which kind of pre-training do you want to do for a particular, which kind of fine-tuning do you want to do for a particular downstream task. So architecture-wise, UL2 essentially there are two forms. There is a decoder-only form and there is an encoder-decoder form. And then the backbone is T5 transformer. So essentially, either it is a transformer decoder or it is basically a transformer encoder decoder model. So architecture-wise, there is not much new in there. So how does this UL2 model perform? So first they trained UL2 models which are sort of smaller in size. So there is a 167 million parameter decoder and a 335 million parameter encoder decoder model. Right. Now also what you see here is that they are comparing how good the UL2 performs compared to 4 other different kinds of baselines. The first one is CLM, causal language model, which is more like GPT, right? The second one is prefix LM. The third one is SC span corruption, which is more like T5, right? Then there is SCLM, which is basically a combination of span corruption and language modeling, right? Both the losses. And the third and the fifth one is basically, of course, UL2. Okay. Now, what you observe is that here, and of course, the results are shown for supervised fine tuning and in context one shot. Okay. So in context learning is also being experimented using the UL2 model. Okay. 4 data sets on which these accuracies are measured. So, SG is super glue. So it's a combination in turn of 8 different natural language understanding tasks. And then there are the 3 tasks from the GEM benchmark, the cross-lingual summarization, SGD schema guided dialogue task, and the third one is the TOTO task, which is table to text generation task. Right. Well, there is also another evaluation which is done on language modeling using the C4 dataset, C4 dataset on which perplexity is being measured. Okay. So for these particular 8 different columns, higher numbers mean better. For perplexity, of course, lower is better. Okay. So what do you observe? You sort of observe that compared to T5, only UL2 decoder is better. So, if you basically look at T5, so which one is T5? This SC, right? Span corruption is T5. So if you compare with that, right? 67.67. You compare these numbers, you typically observe that only UL2 is somewhat in that range, right? So if you basically look at UL2, sometimes it basically gets better than your T5 model also. In fact, in some of those cases, specifically in context one shot kind of cases, T5 model is way better compared to, UL2 model is way better compared to the T5 model, right? Even in terms of perplexity as such. Okay. And then UL2 decoder is better than, in fact, T5 encoder decoder as well. So if you look at the T5 encoder decoder model, in terms of in-context learning, UL2 decoder is actually better even than the encoder decoder model, which is a big deal because UL2 decoder basically is just 167 million parameters, almost half of the T5 encoder decoder model. However, what is interesting is that UL2 encoder decoder is actually better than the UL2 decoder only model. So this the encoder decoder architecture is at least better compared to just the decoder only model. Now, further experiments to scale the pre-training done for UL2. They essentially scale this model from just 335 million parameters to 20 billion parameters. And the way they do this is by having 32 encoder and 32 decoder layers. Right? So they pre-train this model on 1 trillion tokens from the C4 dataset using 512 TPU V4 chips for more than 1 month. The max sequence length, both for input and output, is fixed to 512, and they use sentence piece tokenizer with 32,000 vocabulary. Right. Although I'm not going to discuss those in detail, what is observed is that this UL2 20 billion model actually achieves state of the art on 50 plus NLP tasks. Right. On several different NLP tasks, this model basically obtained state of the art, somewhere around the end of 2022, Yeah. Now, here are some more results about this UL2 20 billion parameter model. So if you do zero-shot learning on superglue, right? So essentially you take the pre-trained UL2 20 billion parameter model, you just do zero-shot pre-training, zero-shot learning, right? Across several different superglue tasks that you see here. And you can compare it with several other previous models which have been popular, right? So for example, a mixture of experts kind of a model, switch transform mixture of experts kind of a model, GPT-3 model, GLAM model, PALM model. There's so many models. These models are sumo-sized models, very large models, right? But these models are somewhere in the range of UL2, right? So basically UL2 is 20 billion parameter, while this model is 13 billion, 8 billion, 8 billion. So this is in the same range, right? And what you observe is that if you compare these models with the UL2 model, 63 is very much in the ballpark of what these same range models can obtain. Right? In fact, it gets sort of very close to PALM 8 billion model. Right? So although so UL2 model essentially, of course, it's a 20 billion parameter model, but the nice idea is that if you really compare it with, let's say, GPT-3 model, right? GPT-3 model is just 61.2, right? Compared with the GPT-3 model, you observe that UL2 20 billion parameter model is better. So that's that. Now, if you also care about few-shot learning, just one-shot learning for cross-lingual summarization, what is observed is that the UL2 model actually beats several other models across different Rouge scores. So UL2 model is better than T5 XXL model, right? And it is better than Lambda model. It is better than PALM model 8 billion as well, right? In fact, yeah, I mean, so PALM model 8 billion is just 7.9 and 8. UL2 is 8.6 on Rouge 2. However, UL2 20 billion is, of course, not as good as PALM 62 billion or 540 billion parameter models. Those are way better. So yeah, I mean, so PALM model, of course, has been pre-trained using way more rigor. But then if you look at other models in a similar compute power range, you observe that UL2 actually performs reasonably well. So what is also interesting to observe is that with standard prompting, you can get some accuracy across different data sets, blue represented by the blue color. But then this UL2 20 billion parameter model also responds to chain of thought prompting. In fact, if you take chain of thought prompting, so these are all mathematical benchmarks. So if you take chain of thought prompting and also allow the model to use calculator so as to solve the computation parts, right? Then the accuracy improves further. And then finally, of course, if you bring in this self-consistency principle along with the chain of thought prompting and the calculator operation, then the accuracy improves even further. So it's good to know that UL2 20 billion parameter model does respond to in-context learning. It responds to a chain of thought prompting, and it also responds to self-consistency. Yeah. So now, so what they further did was to take their UL2 model, and then they took the Flan data set and the instruction fine-tuned using Flan. Okay. So now what was observed is that I mean, of course, when they do this, they obtain a model which is called as Flan UL2. And just like UL2 model, Flan UL2 is also publicly available as a checkpoint, right? The 20 billion parameter model. And what they observed is that on two benchmark data sets, BBH and MMLU, big bench, hard benchmark, and then the several tasks in the MMLU benchmark, what they observed is that Flan UL2 20 billion parameter model is reasonably good compared to several other models. Of course, it's not the best. So, you know, I mean, the Flan Palm models, especially 540 billion, is better. I mean, clearly way better. But then if you compare it with, let's say, OPT model 175 billion parameter, it's way better, right? So 45.3 is way better compared to several of these models. In fact, it is, you know, to a certain extent, it is sort of even better compared to the Flan T5 model, Flan T5 model, right? So if you are basically using Flan T5 model, it's a good idea to switch to Flan UL2 20 billion. Okay, so in summary, in this video, I talked about UL2 and Flan UL2 models. They are based on this principle of mixture of denoisers pre-training. They also have the special token prepended to the input so as to enable mode switching. And that helps associate downstream task behavior with an appropriate chosen upstream pre-training. Right. Several strong results in this paper. So UL2 20 billion achieves state of the art on 50 different NLP tasks. I didn't really talk about which tasks, but they range from language generation to language understanding, text classification, question answering, common sense reasoning, long text reasoning, structured knowledge grounding, and so on, and even information retrieval. Right. UL2 responds to in-context learning. In fact, it outperforms 175 billion parameter GPT-3 model, or even on zero-shot superglue, and it is 3 times better compared to the T5 XXL model on one-shot summarization. Right. So on zero-shot MMLU, I did not talk about it earlier, but zero-shot MMLU UL2 20 billion actually outperforms T0 and T5 models. UL2 20 billion also works well with chain of thought prompting and reasoning, along with self-consistency as well. Lastly, Flan UL2 20 billion parameter model achieves MMLU and big bench hard scores, which are competitive with Flan Palm model 62 billion, right? And it is better than the Flan T5 model. Okay, so I hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.